Right. Hello. Yeah. So far, we have been discussing linear models and scatter plots. Okay. And we are now on pages 97 of your textbook. All right. So let me give a quick recap of what we have covered so far. So all along, this is what we have been discussing. Y is equal to mx plus b. Okay. Now we call this guy. We said this is the slope. Okay. And this is the y-intercept. And the y-intercept is where the trend line cuts the y-axis. So this is the y-intercept. Is that okay? Nice. And now we said the y-axis is called the dependent axis. The dependent axis. And the x-axis is called the independent axis. Okay. Because the value of x are independent, and they determine the value of your y. All right, and we said that to find the slope is found by rise over run. Okay, especially when you're considering that. Okay, so a graph like that. So we have x, and then you have your y, and the rise. So you're talking about changing y. So we are saying y2 minus y1 over x2 minus x1. Is that okay? And this is the formula for finding the slope. And the slope can be interpreted depending on its value. So if you have a negative value, it says that is what? A positive. If you have a negative value, that is a negative trend. So negative is always like that. That's a negative trend. And then if you have a positive value for your slope, then it begins to trend upwards. Is that okay? Nice. So we'll look at how we can interpret the slope further, because that is very, very important. Okay. Now, we also looked at how to find the scope of the model. And we said the scope of the model is where the first dot starts versus where the last dot ends. And you trace it to the x-axis. So the range of values that are there will give you the scope of the model. All right. And you cannot use the model to estimate or to predict something beyond the scope of the model. It's not advisable for you to do that. Is that okay? Nice. So basically, that's what we've been looking at, and we looked at a few examples. We looked at organic milk and inorganic and 2% milk, and we used that as our basis for looking at how to find the slope. Now we want to look at the break-even point. And like I mentioned at the early part of this section, linear modeling has applications in business, in insurance, in so many areas, and we want to see how this can be applied, okay, in other areas of our life. Now, the local Phi Theta Kappa chapter is selling a lemon shake-up on campus as a fundraiser for their trip to Catalyst this year. PTK members are volunteering their time to man the booth, but the chapter spent $90 on supplies to make the shake-ups. They intend to charge $3 per shake-up. Work through the questions below to construct a linear model that will give the profit or loss for a given number of shake-ups sold. Now, what will X and Y represent in terms of the problem? What will X and Y represent? Okay, now X will represent the number of shake-ups sold, and Y will represent the profit or the loss. Is that okay? So X will represent the number of shake-ups and Y will represent the number of loss. Now, what is the slope? And the slope is what we refer to as the rate of change. And the slope has been given as what? 3 per shake-up. Okay, so they intend to charge 3 per shake-up, and that is the slope. Is that okay? So our M is 3. Now, what is the starting point? The starting point is what? $90, and this should be negative because how much you put into a business, you're already starting at a loss position, right? So the $90 is, and it will be a negative number. Now we want to put these together to construct a linear model. All right, now we want to construct a linear model, so we have to get something like that. So we just plug in M for R3X, and then our B will be what? Will be minus 90. So this is minus 90, and that is what we have right there. Is that okay? So that is our linear model. Our linear model is y is equal to 3x minus 90. Is that okay? All right. Now, construct a linear model that represents the money raised by this fundraiser, and that we have done already. But the chapter purchased enough materials to make 225 shakeups. How much money will they have raised if they sell all 225 shakeups? Okay, so because X represents the number of shakeups, you plug in 225 for your X, and they will be able to raise a profit of what? 585, because how much they put in the business, the $90 has been taken out. So 585 is a profit. Now, how many shakeups would they have to sell to raise $300? So this time we have to find our X, the number of shakeups. So we put 300, okay, is equal to 3x is equal to 90, and you solve for X, and they have to sell 130 shakeups to raise $300. Okay. Now, and this is very, this is where we want, this is what we have to know here. The break-even point of a model. When we say you have a business and you broke even at the end of the day, or you did business and you broke even at the end of the day, that means that you neither made a profit nor a loss. So if you bought a TV for $300 and you sold it for $300, that means you've broken even, right? You neither made a profit nor a loss. So here we want to see how many shakeups would a chapter have to sell to break even. Now they need to do that, we have to let our y be equal to 0, because y is equal to 3x minus 90, okay? And 3x will be equal to 90. We divide by 3, divide by 3. So our x should be how many shakeups? 30 shakeups. So the chapter needs to sell 30 shakeups. Is that okay? For them to break even and to get their $90 they invested in the money back. Is that okay? So after 30 shakeups, whatever they sell now will be a profit. Is that okay? Nice. And this is what break even point is all about. Now here, we are going to look at how we can construct models from data points. How we can construct models from data points. And we are going to use the equation, the slope equation, y is equal to m is equal to y2 minus y1 over x2 minus x1. Okay, this is a minus. Okay, now, so first you have to put your numbers in coordinate form. It says in 1980, a pack of cigarettes costs $1 on average. In 2000, the average cost was $3 per pack. So now, how do you do that? So you put this in coordinate form. So you remember I told you time is independent. So time will always be on your x. So you have to put your numbers in coordinate form, x and y form. That's what we call the coordinate form. So for this, in 1980, x will be 1980 and y will be the cost, okay? And then we put this in 2000. So the time will always be on our x and the cost will be right there. So really, if you had to do a graph for that, you realize that this was going to be, the time was going to be here and the costs. Okay, so the time and then the cost was going to be there. All right, so 1980 and then in 2000. Okay, so the time will be on our x. That's why we have, so x against our y. Is that okay? Nice. So that is why we have that. So now this, to find the slope first, it says we should find the slope. This will be our x1, this will be our y1, this is x2 and y2. Now we plug it here. Y2 is what? 3. Y1 is 1. X2 is 2000. And then X1 is 1980. Okay. Now do that. So you're going to have 2 out of 2000 minus 1980. Okay. Let me see. So 2000 minus 1980, and you simplify that. So 2000 minus 1980, and that is 20, right? So really, you have 1 out of 10, and 1 out of 10 is what? 0.1. Okay. So your slope is 0.10 per year. Is that okay? Nice. So you have found the slope. Now it says construct a linear model that predicts the cost of a pack of cigarettes. So now to construct a linear model, you have to do this in this form, right? So you already have your m to be 0.1, and then you attach your x. Now what is your b? Your b is always, if you do it this form, will always be the value of your y, of y1, and y1 is what? 1. Okay, we'll do another example. So your b will be the value of y1. Okay, that goes with the starting here, and that is that, and that gives you your linear model. Is that okay? Now use this information to estimate the cost of a pack of cigarettes today. So 1980 minus, so you have to take, we are in 2020, right? So 2020 minus 1980 gives you 40. Okay, so really what I did here was, this is 2 years ago. Now the current will be 0.10 and 40 plus 1, and that'll give you the pack of cigarette in 2020. Is that okay? Nice. So that is how you do that. So really, to find that, you have to take away the starting year, which is 1980. So 2020 minus 1980, okay, is 40 years. And now you plug in the 40 there, and then you've simplified. Okay. So this should be $5. Okay, sweet. Let's go to the next. Now, the population of a city was 4,800 in 1900. So we have to put this in coordinate form. You have to put this in your x and y form. So this is your x and that is your y. So you have 1900, okay? And then you have 4,800, right? And then in 2005, so you have 2005 and you have 450. So the time will always be your x. So this is your x1, that is y1, x2, y2. Is that okay? Nice. Now, when you do that, you now come back and put it in the formula y2 minus y1 over x2 minus x1. Okay. Now what is your y2? y2 is 450. y1 is 4800. Okay. And then x2 is 2005. And then x1 is 1900. Now when you simplify that, that will give you minus 41.4 people per year. Gucci? Make sense? Right, so that is your slope right there. Now you want to construct a linear model. So in your construction, you have y is equal to mx plus b. Now you have your m as minus 41.4x. Now what is your b? And we have said that your b will always be the value of your y1 if you label it like that. So you have 4800. Okay, and that is that. Okay, so this is the interpretation of your slope, basically. So you say the population decreased by about 41 people per year from 1900 to 2005 because this value is a negative value. That's why there's a decrease. Is that okay? Nice. Okay. All right. Now we want to use the model to predict the population in 2015. So you find the year difference between 2015 and the starting year, right? 1900, and that gives you 115. You plug that in, and that gives you 39 people. Okay. Now, can this trend continue indefinitely? No. According to this model, the town would have a negative population by 2016. So it cannot continue indefinitely. Okay. Nice. Now, we have now looked at how you can find the slope and then find a model, right? Now we want to look at alternative starting year, and in some instances, or you can decide to actually plug in the whole year, okay, without doing the year difference. So for instance, if you went back to this example, you realize that to estimate 2015, we had to subtract 1900 from 2015 to get the year difference and plug that in. So this is just an alternative method. If you want to go by what we just did, that is okay. If you want to use the actual year. But graphically, in some instances, you would have to plug in the actual year, and I will show you how to do that. So this is an alternative method. So to do what we just did. Is that right? So you have to find that and then use the model to find the inset population, and then we will look at that. So here we are looking at the actual what we looked at originally, right? Using so it says that the local population of a certain inset was estimated to be that 4.8 million in 1952. So really you have to do 1952, and this is 4.8 million, right? And then in 2002, all right, 11.4 million. So this is my x1, that is my y1, this is my x2, that is my y2. Now that is how they used to find that. Okay, using the equation m is equal to y2 minus y1 over x2 minus x1. All right, nice. And we want to construct a model because the starting year is 1952. Okay, x will be 0, and that was plugged in, and we have that. Okay. Now we are going to use the same example to look at if we decided to use the actual years. Okay. So here we have to first of all find the b. So you choose any pair of coordinates. So we decided to choose 11.4 million and 2002. Okay. So we plug that into our equation, what the slope we already found, and then we found our B to be that, okay? Now, if you want to estimate for any particular year, because you already, you use the actual years in estimating for the B, if you want to estimate for any year, you have to plug in the whole year. So for instance, if we wanted to estimate for 1992, we plug in 1992 and not yet the year difference. Is that okay? So basically that is how, this is an alternative method. This is how this works. Okay, I'll clarify that, especially graphically when you see a graph that has the actual year versus a graph that has the year difference. Okay, nice. So this is just an example. We want to following the graph. The following graphic comes from a Gallup survey and shows the percentage of smokers in the US between 1945 and 2012. And we're just going to analyze this. Now, let's find a linear model which predicts the percent of US smokers who smoke cigarette from 1978 to 2012. Is that okay? So we are just starting from 1978 to 2012, and that is right there. All right, okay. Now, it says, let the 1978 be the starting year. So we want to look at that, and then what is the y-intercept? The y-intercept is where the trend line casts the y-axis. So when we drew a line, that is the point, and the number here is 38. Now we want to find the slope. To find the slope, we can pick any pair of coordinates over here, okay, and use that to estimate. So what we did here was that to choose 1978 and the corresponding value of our y is 38, and then we chose that 2012 and the corresponding value was 22, right? We labeled that as x1, y1, x2, y2, and then we use the equation to find the slope y2 minus y1 over x2 minus x1, and that gave us the slope. Okay, now we know, having found that, the value of our y1 becomes our b. Okay, so y1 became our b, and that is what we have right there. So we have found the linear model after putting the pieces together. Okay, nice. Now here was the decrease in the percent of smokers in the US constant, or did it vary from year to year? Okay, it varied, right? That is why the graphs are gagged. Okay, now does the model assume a constant decrease or a varying decrease? The model assumes a constant decrease. All right, it's estimated actual change which varies. Okay, now if the decrease had been constant between 1978 and 2012, what would the expected percentage of smokers in the US who smoke have been at the turn of the century? So 100 years. So between that, the century was in what, 2000. So we find the difference and we plug that into our equation to find the estimated percentage of smokers in the US by the year 2000. Okay, nice. And that is how we estimate that. Now you want to use the linear model to estimate the expected percent of smokers who were in the US in 2011. So the starting year is 1978. And between 1978 and 2011, so 2011 minus 1978, the difference is 33 years. So you plug that in and find the percent. Okay, nice. So that was an example, more like trying to connect with what is around us. Okay, now we want to consider the similarities and differences in the graphs below. Okay, so observe these two graphs closely, and we are going to look at the difference. Now we want to interpret the slope. That's the slope. This is the slope, right? The value of the slope. How do you interpret the slope? So you have to interpret the slope, okay, on the context of in the context of the graph. So here, the average global temperatures increased by that degrees Celsius per year. Is that okay? So we are saying it's increased because this value is positive. Now, what does X represent in each of the graphs? So X, if you look at X in the first graph, S represents the years after 1970 in the top graph. So here, this is the starting year. So here you realize the year difference was used. And if you look at this graph, the actual years were used. So really, there's no difference between these two graphs, though they look different. But the difference is that here they use the year difference, and here they use the actual years. And I'll let you know why. And if you look at the y-intercept, you realize that they have different y-intercepts. Okay, and we will see why that is like that. Now use the trendline equation from the first graph to predict the average global temperature for 2016. Okay, rounded to the nearest 100. So for 2016, here we are looking at the first graph. And if you look at it, like I said, on the x-axis, the year difference has been used. So to predict for 2016, you have to subtract the starting year, which is 1970, from 2016. That gives you 46, and you plug that into the equation. Okay, nice. Now, we want to use the trend line equation from the second graph. Now, because on the second graph, we have the actual years on the graph, we don't have to subtract to find the year difference. We just have to plug in the year that is being requested. So we will plug in the whole 2016 into this equation, and that is why there's a difference in the y-intercepts. So you're going to plug in the whole year into the equation, and you get the same answer. Do you see that? So here, what I want to let you know is that if you have a graph that has the year difference and you're asked to estimate for a particular year, okay, and you will always be given this equation. If you ask to estimate for any given year, subtract the starting year from the year that you have to estimate and plug the difference for the value of your X and estimate. On the other hand, if you get a graph that has the actual years on the X and you have to estimate for any given year, just plug in that year for your X like we have done here. So here we didn't subtract, we plugged in 2016 and the results are the same on both ends. This is very insightful and very, very significant. And you're going to see these kind of examples in your assignments. So note when to use what, okay? Okay, good, nice. Now, what is a dependent variable? Would it make sense to reverse this relationship? So it wouldn't make sense. Okay, temperature depends on the year. All right. Okay, so here we look at the breast cancer mortality in Indiana, ages 50 and under. So what we have here is mortality per 100, okay? And we have the years right there, okay? Now we have our linear model right here, okay? We are not supposed to cover this. Somebody will be asking, what is R squared? Okay, R squared. We're not supposed to cover that for now, so I wouldn't bug you with the information. Now, what is the scope of the model? And we said for the scope of the model is where the first that starts and where the last that ends. We trace it to the x-axis. So the scope of the model is between 1975 and 2011. How would you classify this correlation? Is it positive or negative? Now, you realize that this is what? Trending downwards. So this is a negative, a strong but negative correlation, linear model. Is that okay? Now, could you say that the passing of time is causing mortality? No, correlation does not imply causation, right? Changing a calendar year page alone does not save people from breast cancer. And use the linear model to estimate the mortality rate for 2001. So here, because we have the actual years on this graph, we are going to plug in 2001 into this equation for our x. Okay. Now, how does this compare to the actual mortality rate for 2001? So we want to look at the actual mortality rate for 2001. And the actual is what on the graph. We compare the two values and you realize it appears to be lower than the value in the graphic. Okay, nice. Now, use the linear model to predict the mortality rate for 2015. Again, you plug in 2015 into your equation and you have 4. Okay, now what is the, which will the model be accurate for 2015? No, because 2015 is outside the scope. The scope ends there, right? So 2015 is outside the scope of the model, so it wouldn't be accurate, though we can estimate. Nice. So here, you remember we did absolute changes, and you just want to find the absolute change, which is the new minus the old, okay? And you use those to kind of explain these, right? Nice. So here, basically, we have covered almost everything, and this is just Excel applications using Excel for scatter and linear models. And you have the instructions as you see right in your book, so give it a try, okay? And give me your feedback. If you have concerns, let me know, and we look at it. So I want us to look at this example on firearms, and then we'll go through the practice so that you can get more examples. And here, so firearm rate per 100,000 in 2013, and these are percent of population that are registered gun owners, and the number of firearm deaths per 100,000. So this, so really Indiana, so here we have to use proportions, okay? We want to find how many firearm deaths were there in Indiana. We want to round to the nearest whole number, okay? And we do that. Now discuss the mathematical trend of this data. What does the trend mean in context? So there's a positive trend, meaning the higher the percent of registered gun owners, the higher the number of firearm deaths. Okay, we want to classify the correlation as either weak, moderate, and this is moderate, right? And does this mean that owning a gun causes firearm deaths? No, this correlation does not imply causation. The fact that I own a gun doesn't mean that I want to, take somebody's life. Okay, nice. So that is how you discuss a graph of this nature. All right, now here, these are practice problems, and I would want us to go through these practice problems one after the other. Now, leasing a particular car costs $850 plus a monthly cost of $225. We want to create a model that gives the total cost for a given number of months leased. Now, what would the dependent variable y represent in our model? Tell me. So you realize that the cost of the lease will be your y. Is that okay? And measured in dollars. Now, what will the dependent variable represent in the model? And the dependent variable represent the lease time measured in months. And what is the starting value for the lease? What is the starting value? And that has been given as what? $850. Leasing a particular car costs $850 plus a monthly fee of that. Okay. Now we want to put these together. What is the slope? And the rate of change is our slope plus a monthly fee of what? So every month, cost per month is what? 225, and that is our slope. Now we want to put these pieces together, and this gives us a linear model. Now, how much would it cost to lease the car for 6 months? Okay, for 6 months, so you have to plug in 6 for your X, and that will determine the cost, how much you pay in 6 months. Now, if your budget is 3,800, you want to find how many months you can lease the car for. And you can lease the car for 13 months. Okay, good. So basically, that is it. The Happy Widget Company has a fixed cost of $1,500 each day to run their factory, and a variable cost of $1.25 for each widget they produce. So we want to create a model for this, and this is the rate of change. That's our slope plus the first cost of $1,500. Now, how much will it cost to produce 300 widgets? And it will cost 1,875. How many widgets? You want to find X, okay? And that is 432. Okay, so basically, this is how you go about this example. Okay, so if you're asked to interpret the slope has been given right there. And you interpret the slope as that. Since 1909, meat consumption per capita has been increasing by about 1.05 pounds per year, okay? And you want to use the linear model to estimate the meat consumption for 2010. And because you have the actual years on your X, you plug in 2010 into that equation for your X, and you find that, okay? So basically, that is the end of our discussions on linear models. Okay, so thank you very much for your time, and I'll see you soon. Bye-bye.